Okay, so this is problem number 33 from chapter 6. Here's the situation. We have two blocks. This little dude has a mass of 16 kilograms. This guy has a mass of 88 kilograms. They're not attached to each other, but we're told about the coefficient of static friction between the two blocks, so that's right here. But then we're also told that the surface underneath is frictionless. We're trying to solve for this force F that is pushing on the smaller block to keep it from slipping down the larger block. So I've started already drawing a free body diagram of our whole system right here, because here's the situation. If you read this problem, a lot of students get stuck because they have no idea what to do. But if you have no idea what to do, you should draw a free body diagram if there's any forces involved. And so that's what we've done. So here's that force F. There's our normal force. That's from this pushing down on the ground. Here's the weight. And the forces that would be, and you don't need to be concerned with what is the weight of, whether it's both or just one. I know that's kind of weird, but fortunately we don't have to deal with it here. So let's just call it the weight. We have an internal force right here, but since that's internal, I'm not going to include it. And so then, as per usual, I know that F equals ma. And so I'm going to sum the forces in the x direction. And we notice the only force in the x direction is that force F. So we're like F equals, but then of course, since our system is the whole thing, that's going to be m plus m times a. Now, this is what we ultimately want to solve for. And we know little m, we know big M, we don't know acceleration. So what I would do at this point is I would break these into two different free body diagrams and see what we can figure out, because there's several different ways to go about this. So let's just do it. I'm going to make a free body diagram of the smaller guy, and I'm going to make it red so that we can distinguish what's going on with all our different stuff. Also, be careful that you distinguish little m from capital M so that it is clear to you how they're different, since one is 16 kilograms and one is 88. So in here, let's draw all of our forces. Of course, we have this F that's right there because it's physically touching our block. I have the weight, so that will be little mg. We have friction, and in order to consider what direction friction is going, what I would recommend is think about what way would this go if there was no friction, and hopefully it's intuitive to you that it would fall down, and since friction opposes motion, friction will be going up. So we have static friction, which of course means that we're not moving. And then what else? We are also pushing onto this big block. And so there's going to be a force from the big block pushing back onto the little block. So I'm going to call that Fm, because it's force from my M block. So there's that. Let's draw our bigger one while we're doing free body diagrams. So here is big M. And for this one, I'll have the normal force since it's touching a surface here. I will have the weight, so capital Mg. I will also have the force of the little block touching the big one. So that is F from little m. And what you might notice here is that these are our internal forces. And so the magnitude of F big M is the same as F little m. So I'll write that right here. Fm equals Fn, which is going to be important later. One place that students get confused sometimes is they want to put this force F onto this free body diagram. But you may not do that. You may never do that. And the reason why is because this force is touching our smaller block. It is not touching our larger block. The thing that's allowing our larger block to move is only the fact that the smaller block is touching the larger block. Other than that, it wouldn't move. And so you cannot include this big force on the free body diagram for our big block. We also are going to have the equal and opposite force to this Fs. So that's going to be here. I'll put that in quotes because it's the same magnitude as this, but opposite direction. Also, this is not really going to matter, but some people got kind of confused because they wanted to include all of the internal forces. So there you go. That's equal and opposite to that guy. All right, let's do some F equals MAs, see how things go. So for this little dude, sum of the forces in the x direction will equal mass times acceleration. So I'm going to consider to the right to be my positive direction. So I have F minus Fm equals little m times A. And then in the y direction, still, we know that F equals ma, but we know in the y direction, since we are going to prevent this from slipping, our acceleration is going to be 0. So I will have Fs minus mg equals to 0. So Fs equals mg. So hooray for us. We have a couple new equations. And with this old equation we're getting pretty close to being able to do something useful. I'm going to just do a couple more equations, or one more equation right here. So sum of the forces in the x direction equals big M times A. And so in the x direction, the only thing we have in the x direction for this blue free body diagram is this Fm. So Fm equals ma. We could sum of the forces in the y direction, but these are a whole bunch of things that we don't really care about. And so I'm not going to worry about it. So we have this, and we have this. And so let's see. Let's break this down a little bit more, because we know that we're given the coefficient of static friction. And so if that's the case, we probably should use it. And so we know that friction is mu s times our normal force equals mg. However, this is also a place that students get confused, because they're like, oh, normal force, is that this normal force? Should there be another random force going up from here? And the answer is no, because remember, normal force is the force from where a surface is pushing back onto the object. That force of the surface pushing back onto the object is the normal force. So in this case, my Fm is the normal force, because this is the force that is pushing on the surface to which my friction is perpendicular. And so this is my normal force. And you can hopefully intuitively understand that, because if I were to push with this force a lot more, have a much bigger force, then that means that this would also be bigger, and therefore my friction would be bigger, in the sense that it would be harder to slip down. Or similarly, if I had a much smaller force there, then this would also be smaller, and it would be much easier to slip down, so less friction. So these are directly related. So now I can write mu s times Fm, because that's my normal force we determined, equals little m times g. So now let's revisit what we're actually trying to figure out. We are trying to figure out what is this force F. And so I have that force F here, and I have that force F here. And there are several different mathematical ways to go about this. I'm going to do what I consider to be the easiest. And so my next step is I would notice that this Fm is something I don't know. And so then I'm like, okay, well, then I'm going to have to use one of these two equations to plug in for that and essentially get rid of that variable. And between this red equation and the blue equation, the blue one looks easier. So I'm going to go with that. So from here, I'll have mu s, and instead of times Fm, I know that that equals ma. And so, and again, be careful about your capital letters here, so you know what you're doing. And that equals to mg from this equation. But now we have two problems. Problem number one, the equation that we have does not have an f in it, and that's what we want to solve for. Problem number two, we do have an a, and we don't know what the acceleration is. Quick note, the acceleration here and here and here are all the same acceleration, because it's moving as a unit together. So that's helpful. But since we have a and we don't want it, and we don't have f and we do want it, I'm going to go over here. I would not choose these, because these, again, have the variable that we don't want. We don't know Fm, but we want to know f. And so over here, I will note that a equals f over m plus m, and now I'll take this and plug it in for my acceleration. So I'm going to just use one color now of mu s times m, and then that a is, of course, f over m plus m equals mg. And from here, I'm just going to solve for my f to get that alone, since that's what we're trying to solve for. So f equals mg, m plus m over mu s times capital M. Now if I were to plug some numbers in there, I have 16 times 9.8 times 16 plus 88 all over 0.38, that's our mu that was given, times 88. And if you plug this into your calculator, you will find out that your force equals 488 newtons. And we did it.